Hello everyone. Can you hear me? How you all doing? Just let me know in the chat if you can hear me properly, so I can go ahead. Hello Rahul. हाँ कृष्णकांत आ गया मैं. Let me know in the chat if you can hear me. Please just drop a text in the chat. So I just want to make it clear. Rahul or Krishnakant or anyone in the chat, can you just drop a yes? I can hear you in the chat. Hi Pawan. Am I not audible? Awesome. Thanks, Ron. Awesome. So, good morning, everyone. I'm Sai Vinash, and in this class, I'll be taking like a little more. I'll take a step ahead in combinatorics, and I'll teach you how to compute factorials and binomial coefficients. I know I've touched about this in the previous class once, but I'll show it to you again for those who haven't. And apart from that, I would be teaching about computing large binomial sequences efficiently. And I'll be teaching two sequences. One is a summation and one is a summation of products. Apart from that, I'll be teaching a slightly tricky combinatorics problem, and I'll be teaching three ways of doing it. I believe that like solving a problem three different ways is from that you're gonna learn a lot more than solving three different problems in one way. Well, yeah, like you're gonna get like in-depth knowledge about binomial like combinatorics and so on. Thanks, Rahul. So a little about myself. I am currently working as an SRE SWE at Google Dublin. My all India rank in CodeChef is 3. I'm a 7-star coder there. My max, I'm max international master in CodeChef, in Codeforces, and I'm currently a master there. I'm an SD intern at Uber, and I'm a Snackdown finalist. And if you, and my nickname is Sinus_070. The subjects that I take are discrete maths, dynamic programming, and graphs, and a lot more competitive programming topics. So use the code SciLife on the Unacademy Pro subscription. So career as a software developer subscription, it's an interesting show covering a variety of topics. It shows around live problem solving and over the weekend projects. So live problem solving, I'll show it in the next slide. And over the weekend projects is taken by Raj, one of the famous YouTubers in India. And he's gonna go through your projects and he's gonna really concentrate on what needs to be improved and so on. Who should buy this subscription? The enthusiasts in software and technology domain who want to enable lifelong learning. Like if you really want to learn like core topics in computer science, this is the right subscription for you. So use the code SciLife to get 10% off on the Unacademy Pro subscription. It's just $9.99 per year. It's not really expensive either. Hello, Vinay. So, college projects, as I said, it's a show every Friday night at 10 p.m. It starts on 6th August. It's already started. It's taken by very own Raj Vikramaditya Striver, and he's a really famous YouTuber, as you might have already known. And he's going to go through your college projects, and he's going to say if it's eligible for internships, or like how good is it for internships, and what needs to be improved, and what are the other things that you can add to your project to make it more fruitful. So he's an SDA at MediaNet and a 6-star at CodeChef, and I think it's really going to be cool. So do check it out. So there's a CodeChef Apprentice that I've already started taking. It's a show that goes live every Saturday afternoon at 2 p.m. Now in this show, I'm going to pick a student or any beginner computer programmer who's like struggling to improve, and I'm going to take his case and I would like ask him to narrate his experience and narrate his blockers or where he's blocked and which topics are difficult for him, and I'm going to suggest a Akshay, yes. Krishnakant, I'm great. How are you? So I'm going to take a student and exactly explain him what needs to be improved, and like how can he go about it so that he can improve very quickly. And apart from that, I'll also be taking one or two problems, and I'll make him solve it, or make him or her, or I would solve it in front of them. Like, depends on the problem itself. This show is, if you're a beginner, this show is really suitable for you, because as a beginner you might run into a lot of blockers, and when I'm kind of mentoring that person, there will be things that are relatable to you too, and which are applicable to you too. So if you think that's going to be useful to you, do check out the Career as a Software Developer subscription, and don't forget to use the code SciLife. And it's taken by me, and again, I've discussed about myself. It's going to go live this Saturday afternoon at 2 p.m. So yeah. So if you think this content is going to be useful to you, do like and share it to your friends. With like, if you think it's going to be useful to them too, and if they started competitive programming or something, share it with them. And as I said, if you think this content is going to be useful to you, subscribe, because there's going to be a lot more coming. So a lot of you have asked me how to compute factorials and binomial coefficients in the last class. Yeah, Nitin, I went to BITS Goa. It's in Goa, as the name suggests. So computing factorials and binomial coefficients. I'll get to this real quick. Like it's really, since I've already explained it, I'll just explain it to you real quick. One sec. So let's just revise what factorials and binomial coefficients are. This is the last class. Awesome. So factorial, a parameter for a factorial is just one number, one like non-negative integer, and it's represented by n factorial. And n factorial is just 1 into 2 into 3 into 4 into so on till n. It's a number of ways you can arrange n distinct objects. Alright, okay. Now, this is factorial. Factorial, as we discussed. So, I don't want the upgrade, man. Alright. Now, what's a binomial coefficient? It's given by, like, it's two integers are the parameters, n and r, where 0 less than equal to r less than equal to n, and both are positive, both are like non-negative integers, and it's given by the notation n choose r. This is just, and this is n factorial by r factorial into n minus r factorial. All right. Now let's look at how we can compute them quickly. Yeah, when I know it's discussed, I'm just doing a quick revision. Last time people have asked me, so it's just going to take under 5 minutes. So just bear with me. I'll just const and max equals, say I want to do compute it till 1e6, and what do? And it's discussed, and I know, and I'm using this to solve different problems too. So I'll keep the code here. So I'd like to explain my code every time I write it. Void compute factorials. So factorials are compute, since factorials can grow really quickly. Like for example, 10 factorial is about 30,000. I think 3 lakhs or something. And but 100 factorial can just go above the limits of integer, what your computer can hold in the long, like what C++'s limit is in the long is only up to 10 power 12. All right. So since 100 factorial can grow too high, we take mod const ll mod equals 1e9 plus 7, mod a prime number. So compute factorials is just we store the numbers in a array, ll fac max n. So what we do is we declare the base case equals 1 for int I equals 1, I less than max n, I plus plus, fac of I equals fac of I into factorial of I equals factorial of I minus 1. Since when you are at factorial of I, all the lower factorials are computed, we just multiply this by modulo mod. Now we do compute factorials, and this just runs in O of n simply. Alright, this just runs in O of n. And once you do this, this is going to take 10 power 6 operations, and every subsequent factorial, say if you want to compute 5 factorial or 25 factorial, see out fac of 25 will give you the answer directly in O of 1. Instead of computing a factorial each time, like if you want to compute it exactly once, like without any pre-computation, without this, it would take O of n time for each factorial. So that might take a lot of time. So doing this once and for all is going to be friendly time-wise, efficiency-wise. All right. Now, how to do n choose r? So what do you do in n choose r is very straightforward. We use the Fermat's theorem here. We use the Fermat's theorem. And what's Fermat's theorem? A power p minus 2. Let's go step by step. A power p minus 1 is 1 mod p. So what's a power minus 1? So which means a power p minus 2 is equal to a power minus 1 mod p. We are dividing by a at both sides. A power minus 1, I know for those who aren't familiar with Fermat's theorem, a power minus 1 is a number such that a into a, like if b is equal to a power minus 1, then b into a mod p equals 1. Got it? A inverse into a. A inverse is just a number where if you multiply it by a, it should give you 1, right? That's what it means. In mod p, it means that b into a should be gives a remainder 1 modulo p. Now, what this means is, note that you need to know what Fermat's theorem is, like to understand this. So, n choose r is just n factorial by r factorial into n minus r factorial. Got it? So we can also we need to compute this modulo p, right? Like the chances are, if the factorial is going to be huge, they won't ask you to compute the right factorial. They're going to ask you modulo prime in any problem, which means you can write this as n factorial into r factorial power minus 1 into n minus r factorial power minus 1, which means that we can use Fermat's theorem to compute this. N factorial into r factorial power p minus 2 into n minus r factorial power p minus 2. And we're going to just multiply all of them. Any doubts so far? I'll just write, or we can just store all of these factorials in an inverse factorial number, n factorial of r. We compute this. N factorial of r. N minus r. So what I'm doing here is inverse factorial. This is basically 1 by factorial. This is only so that I compute it quickly and no other reason. In factorial of 0, 1 by 0 factorial is just 1. In factorial of I is equal to inverse of factorial of I, fac of I. And we'll discuss what inverse is here. Inverse, we know what inverse is. Inverse of x is x power p minus 2. For that, we need to write what power function is. LL power of a comma LLA comma LLB. This is a power b. A to the power b mod. So if b equals 0, this is binary exponentiation, return 1. If b modulo 2 equals 0, LLX equals power of a comma b by 2, return x into x modulo mod. We know this, else return. Same thing comes here. Since x is odd here, we return answer equals x into x modulo mod, return answer into b. answering into a modulo mod. Because in this case, b is odd here, and when you do b by 2, one number is shaved off, one a is shaved off, so that's why you multiply that to equate it. Got it? Alright. Now, inverse, LL inverse. We discussed what an inverse is using Fermat's theorem. Return power of a comma mod minus 2. Simple, that's it. Now, there are say t. Now, when we want to compute this factorial, and n choose r, which is LL, NCR, LLN, LLR. Now, if n is less than 0 or r is less than 0 or r is greater than n, return 0. Factorial is only defined if n is a non-negative integer and r should be between 0 and n. Got it? Now then return LL answer equals fac of I into inverse fac in fac of I n factorial. Let's compute the numerator and denominator separately. Numerator equals factorial of I. LL denominator equals I fac of I inverse fact of n. It's n r into inverse fac of n minus r. You take mod at each step you are multiplying. Return numerator into denominator. Is this clear? This is basically computing n choose r. The pre-computation is O of n. This is going to take O of n, like O of max n, 10 power 6, which is okay. 10 power 6 into log 10 power 6 because inverse is being taken. This is a slight trick where you can improve, but it's not worth it. So I'm not going to go there. And when we're computing n choose r, this is n factorial, and we're multiplying it by this n factorial by r factorial into n minus r factorial. Is this clear? Any doubts so far? Do you want me to re-explain something? Anyone, any doubts? Krishnakant, Rahul, Pawan, if you have any doubts, please let me know in the chat. When I understand you got it. I'll move on to the next topic very quick because we already discussed this in the last class. So, any doubts so far? Computing n choose r is just O of 1. This is an O of 1 check. This is n factorial, and this is again O of 1 factor. O of 1. We're multiplying, that's also O of 1. Any doubts? If you want me to explain this again, I can explain it to you. Okay, inverse factorial is not clear. Okay, so what is inverse factorial doing? So, I'll just explain it for once and then we'll move on to the next. So, inverse factorial, we know that NCR is equal to n factorial by r factorial into n minus r factorial, right? Alright. Now, we can write this as n factorial into 1 by r factorial into 1 by n minus r factorial. Now, inverse factorial of r is storing 1 by r factorial. Inverse factorial of n minus r is storing 1 by n minus r factorial. Yep, I'm repeating it. I'm repeating, no worries. Inverse factorial of r is storing 1 by r factorial. Inverse factorial of n minus r is storing 1 by n minus r factorial. And we know that 1 by r factorial modulo 1 by r factorial is just r factorial power p minus 2, right? Using Fermat's theorem. If you aren't familiar with Fermat's theorem, I suggest you to go to my other number theory videos and just look at it once. So that's what I'm storing. Inverse factorial of r is just r factorial power p minus 2. Inverse factorial of n minus r is n minus r factorial is just like n minus r is just n minus r factorial power p minus 2. That's what I'm computing here. And then I multiply all three. So as you can see here, inverse factorial of I is inverse of factorial of I. And inverse function is just power of a comma mod minus 2. This is basically the prime minus 2. So I'm computing all inverse factorials and all factorials. And then when I'm asked to calculate n choose r of I, like n choose r, I'm first computing factorial of n, then I'm computing inverse factorial of r and inverse factorial of n minus r, which is basically I'm computing this and multiplying it by this, and then I'm multiplying all three together, like an factorial n factorial into 1 by r factorial into 1 by n minus r factorial. Is this clear so far? Do you want me to repeat it? Like, is this do you understand this? Now, when you want to calculate n choose r, we can just call this function. Any questions so far? Do you want me to explain any part again? Like, if there's any part which is not clear, could you please mention in the chat? You really need to get this clear to understand, to like solve a lot of combinatorics problems. Like, you might be able to solve it, but you need to code it as well. So this is very important. Awesome, awesome. Understood? Like, is everything clear? Anyone, any doubts? All right. So without any further delay, I'll move on to the next topic. Efficient summations. Like in some problems, you might be asked to calculate n choose n plus 1 choose n plus n plus 2 choose n, and so on to n plus k choose n. How would you do this? How would you do this? So Deepak, will you teach whole DSA? Hiran, first I'll answer Deepak's question. Will you teach whole DSA means from basics to beyond? See, I can tell that I'm teaching basic DSAs from complete DSA, but I would be lying because you can't cover basic DSA in a month or 2 months. So what I'll teach you is how to solve problems. So there's this common saying that if you, I don't know if I got it right. So if you just give a fisherman, just like lend a fisherman some food, then it'll feed him for a day. But if you teach a person how to fish, it'll feed him for his whole lifetime. So I'll teach you how to solve problems, and you can learn the simple topics on your own. But problem solving and applying problem solving is what will help you solve harder problems. So I'll just teach you how to solve problems. Is that understood? And how much it takes to compute n choose r? It takes, as you can see here, it takes just O of 1. Once the pre-computation is done, pre-computation is just O of n. This is just O of 1 here. This is O of 1. This is O of 1. Multiplication is O of 1. Or multiplication is again O of 1. So what is this? N choose n plus 1 choose n. Yep, Rahul has got it right. Here on, I hope that's clear. It's just O of 1. So what is the computer? What is it asked to? Yes, that's O. But since that's already stored in an array, like we have pre-computed that. Understand? We just pre-computed that. So it takes n log n, O of n log n pre-computation. We can make it O of n. That's a slight optimization. You can look at it in my previous number theory videos. It's that, but it's really not required. Like if O of n log n passes, O of n usually passes a lot of times. Yeah. Now let's look at this problem without further delay. What does this problem ask? It asks you to calculate n choose n plus n plus 1 choose n plus n plus 2 choose n plus so on n plus k choose n. We can write n choose n. Since n choose n is 1, we can just write it as n plus, this is just 1, right? We can just write this as n plus 1 choose n plus 1 as well. And more importantly, we write this as first, we can write this as n plus 1 choose 0. Correct. This is 1, n choose n is also 1 because n factorial by n factorial, that's 1. N plus 1 choose n, we know that n choose r is also equal to n choose n minus r, right? So this is going to be n plus 1 choose 1 plus n plus 2 choose n is n plus 2 choose 2, same thing, plus so on till n plus k choose n. Fair. Now n plus 1 choose 0 plus n plus 1 choose 1. So what did we discuss about this in the last video? So NCR is equal to NCR minus 1, n minus 1 CR minus 1 plus n minus 1 CR. Meaning, if you want to pick R objects from n objects, it's as same as you either pick the last object, which means you're picking R minus 1 from n minus 1, or you don't pick the last object, which means you have to pick all R objects from the n minus 1 objects. This is the identity we discussed in the last class, correct? Now, we're going to use that. So n plus 1 choose 0 plus n plus 1 choose 1. This is going to give you n plus 2 choose 1. Instead of n minus 1, put n plus 1 here. Then you get n plus 2. So what I'm doing here is n plus 1 choose 0 plus n plus 1 choose 1 is equal to n plus 2 choose 1. So now from here we get n plus 2 choose 1 plus n plus 2 choose 2 is equal to n plus 3 choose 2. And now n plus now and so on. That is, we just discuss. N plus 1 choose 1 plus 1 choose 0 plus n plus 1 choose 1 plus n plus 1 choose I screwed up. N plus 2 choose 2 plus n plus 3 choose 3 plus so on, n plus k choose k. Now this comes out to be n plus 2 choose 1. Now this, you combine these two, you get n plus 3 choose 2. Combine these two, you get n plus 4 choose 3, so on. So if you combine the last one, you can see n plus 3 choose 3 till n plus 3 choose 3 it become n plus 4 choose 3. So till n plus k choose k, it will become n plus k plus 1 choose k. Simple. That's the solution. We recursively keep adding n plus 1 choose 0 plus n plus 1 choose 1, you get n plus 2 choose 1. Simple. N plus 2 choose 2 plus n plus 2 choose 1 will give you n plus 3 choose 2. N plus 3 choose 2 plus n plus 3 choose 3 will give you n plus 4 choose 3, and so on. So till n plus 3 choose 3, we got n plus 4 choose 3. So till n plus k choose k, we get n plus k plus 1 choose k. Is this clear? Any doubts so far? Like previously we did it in a long boring way. We had to compute each one by one. N plus 1 choose 0, n plus 1 choose 1, n plus 2 choose 2, and so on. It was really boring. But now there's just one. You need to just compute one factorial, one binomial coefficient. That's it. Instead of computing k binomial coefficients, computing one is sufficient. Yes, we are using n choose r plus n choose r minus 1 is equal to. That's I think that's slightly yeah, exactly. N choose r plus n choose r minus 1 equals n plus 1 choose r. That's correct. Any doubts so far? All clear? If you have any doubts, please let me know in the chat. Things like this are important. Any doubts? Like any point you have any doubts, please just write it in the chat. I'll just go back to that point and I'll teach that point again for you. Awesome. Let me move on to the next summation. This seems a bit overwhelming, but it's not, trust me. Sum of n choose I into m choose k minus I. What does this mean? Sigma, I'll just write sigma, n choose I, m choose k minus I. So given n comma n comma k, n, m, k. Don't get worried about sigma, like sigma, k, I and all, like I'll tell you what it means. So sigma, n choose I, m choose k minus I equals 0 to k. What this means is, say n is 2, m is equal to 2, 3 and k equals 4. It means that 2c0, first put, this is essentially, if k equals say 4, 4 might be too much, one sec, let's say 3. So this would be I equals 0, I to 3. Rinkesh, the time complexity before would be O of k, but see, in some problems you might have a lot of test cases where in each test case you have to compute the summation, which means each test case will be O of k. Now, after reducing it to a single term, each test case will be O of 1. So with the pre-computation that we did here, we can compute each test case in O of 1, right? Previously, we had to do in each test case, like we had to do it in O of k, which might be too much. So after computing this whole thing, we just need to compute factorials and inverse factorials till O of n plus k. Like it might be usually under 10 parsecs or something. We already have pre-computed it. So this whole thing we can just compute in O of 1 because I think last question your answer was different. Did you get n plus k plus 1 choose n plus 1? Yep, it is correct, right? N plus k plus 1 choose n plus 1. N plus k plus 1 choose n plus 1 is same as n plus k plus 1 choose k. So it is correct. Yes. Yes, Vinay Neelam Shetty is correct here. Like I can show you in a more visualized way here. What this means is n choose I into m choose k minus I means and this is basically 2 choose I, 3 choose k, 3 choose 3 minus I, which is basically 2c0 3c3 plus 2c1 3c1 3c2 plus 2c2 3c3 plus 2c3 3c. One sec, I screwed up here. 3c1 plus 2c3 into 3c0, but this is invalid, so this becomes 0. So basically the summation. Okay, now how do you compute the summation? Look at it closely. So there are two boxes. I'll give you more visual interpretation. What Vinay said is also an explanation, it's a valid explanation. That's one of the proofs for it, but I'll give you a more visual explanation. Say you have 2 balls in this box and 3 balls in this box, numbered 1, 2, numbered 3, 4, 5. So 2c0 and 3c3 represents the number of ways to pick 0 balls from this and 3 balls from this, correct? 2c1 and 3c2 like represents the number of ways to pick 1 ball from this and 2 balls from this. 2 choose 2 into 3 choose 1 shows you the number of ways you can pick 2 balls from this and 1 ball from this, like which is basically 1 into 3, the 3 ways to pick 1 ball and 1 way to pick 2 balls. 2 choose 3 into 3 choose 2, 0 represents the number of ways to pick 3 balls from this ball and no balls from this ball. Since you can't pick 3 balls from 2 balls, that's not possible. So this will become 0. That's what this represents. So in essentially this represents what this represents is one sec. You're taking, there are 2 buckets, there are n balls here, and in another bucket there are m balls. Now n choose I, m choose k minus I. Multiplying them represents the number of ways you can pick I balls from n balls and k minus I balls from m balls. Since you're doing them independently, we multiply them. Now this translates to, and if you sum it up for all I, you either pick 0 balls from the first bucket or k balls from the next bucket, or 1 ball from the first bucket, k minus 1 from the next bucket, 2 from the first bucket, k minus 2 from the second bucket, and so on. What this translates to is, say we have all the n plus m balls here, it's as good as picking k balls from this, right? Meaning, let's label the first 1 to n balls as 1 to n, let's put the first n balls in the first bucket, next m balls in the second bucket. Now this summation is basically telling you, okay, we either pick 0 balls from the first bucket and k balls from the second bucket, or we pick 1 balls from the first bucket, k minus 1 balls from the second bucket, and so on. It's as good as picking, if you add them all up, it's as good as picking k balls from a bucket of n plus m balls. And that translates to, and we know that that translates to n plus m choose k. So this summation is counting the number of ways to perform, split it into 2 buckets and picking and solving for each case. Like there are only k cases, k plus 1 cases, like either you pick 0 from first ball and first bucket and k from second bucket, 1 from first bucket, k minus 1 from second bucket, and all those cases, you add them up. That's what the summation represents. And another way to compute that is, from a bucket of n plus m balls, you pick k balls. Both should be equal, right? Since you're computing them correctly, both the summations should be equal to each other. Understood? So is this understood so far? Any doubts? So this summation is simply equal to n plus m choose k. Any doubts? Do you want me to explain it again? Any questions? Like if anything's not clear, can you please let me know so that I can explain it again in a way that's understandable to you. Rahul, Vinay, Pawan, so on. Like, can you tell me if it's clear? So if this is not clear, I'd really like to explain it to you again. Awesome. Awesome. So all clear, right? So I'll move on to the next topic if it's clear. So essentially what we did is, what we did was, like, I'll just revise it one small time and then we'll understand. Awesome. Sigma n choose I, n choose k minus I. Awesome. All of you guys understood. N choose I, n choose k minus I is simply, n choose I, n choose k minus I is just picking I from the first n balls and k minus I from the second n balls, and we are doing this for all I, which means we are covering all cases, and when we sum them up, it's as good as picking k balls from n plus m balls, which is equal to n plus m choose k. Now there is another mathematical way. This is another mathematical way which Vinay just mentioned. Instead of x plus y power n, I'll take 1 plus x whole power n. We know that this is equal to n choose 0 x power 0 plus n choose 1 x power 1 plus n choose 2 x power 2. We discussed in the last class. So until n choose n x power n, or even if we didn't discuss, it's high school math. Now 1 plus x whole power m is equal to m choose 0 x power 0 plus m choose 1 x power 1 plus so on till m choose m x power m. Fair. Now when we multiply both of them, let's look closely at the coefficient of x power m when we multiply both of them. So coefficient of x power m plus n would be x power 0 from the first term. I just meant coefficient of x power k when we multiply both of them will be x power 0 and x power k in this, which means nc is 0 into m choose k plus x power 1 into x power k minus 1, n choose 1 into m choose k minus 1. Here we take x power 2 and here we take x power k minus 2. We get here n choose 2 into m choose k minus 2 plus so on. Yeah, coefficient of x power k, I told that, yeah, and so on. That's what we get if we multiply both of them. And another way is, if you multiply both of them, it's same as 1 plus x, coefficient of x power k in 1 plus x whole power m plus n. We know that coefficient of x power k in 1 plus x power m plus n is m plus n choose k. So this has to be equal to this because we computed them in two correct ways. Is this clear? Any doubts so far? Do you want me to re-explain something? Is this clear? Would someone like to, does anyone want me to re-explain any part of it? Can you be more specific which part I need to re-explain? Or if it's clear, let me know it's clear in the chat so that I can move on to the next topic. I know it might sound a lot of math, but this is useful math, so. All right. I'll move on. So just to emphasize the use of this. Previously, say we had to compute for t case. Let's say for t test cases, you're given n comma m comma k, and you had to compute sigma n choose I, m choose k minus I equals 0 to k. Previously, say we had given t test cases, t is up to 10 power 5, n comma m comma k are less than 10 power 6, 10 power 5 assume. What did we have to do here? You have to compute while for each test case 0 I less than t, I plus plus ll n comma m comma k. We can just take integers c n m k. For int I equals 0, I less than equal to k, I plus plus. We had to compute answer equals answer plus NCR of n comma I into NCR of m comma k minus I. This is the brute force way. This is just to show you what to emphasize. Modulo 1. For multiplication, I'm taking the modulo, and for the whole addition as well, I'm taking the modulo. Here on, it is possible, but in this case, we are taking them as different just so that we get the solution correctly. Like, we are assuming that different just so that we can, then it won't be m choose n, m plus n choose n. Like, that would be a wrong way of doing it because it can be same, but like if they're different, we can reduce it to a more cleaner form. Hope that's clear. See out answer. Right. Now this, you can see that this is for each test case we are doing O of k. So the total complexity would be O of k, O of t into k, which would be really bad. Instead, what are you doing is answer equals, after in the reduced format, we're just doing m plus n choose k. This is O of 1 and total would be O of t. So this is, now we are being way more efficient than we used to be. That's the problem we are solving here. All right. Awesome. Any doubts so far? If there are any doubts, please let me know in the chat, and if it's clear, do let me know that too. I shall move on to the next topic. Next problem instead. I really like the problem because it has these, it has multiple approaches. Awesome. Awesome. Next problem. So, there are 2n players participating in a tournament. Find the number of pairings Pn for the first round. Order of the rounds doesn't matter. What does this mean? What does this mean? 2n players are participating in a tournament. Find the number of pairings Pn for the first round. Meaning, let's say n equals 3. n equals 3. 2n players, which means 6 players. Call them 1, 2, 3, 4, 5, 6. Find the number of pairings for the first round. What is a pairing? And the order of rounds doesn't matter. One such pairing is 1, 2 player match, 3, 4, 3, 4 player match, 5, 6 player match. This is one such pairing. Note that this pairing is same as 1, 2, 5, 6 and 3, 4 because the order of the rounds doesn't matter. 5, 6 and it's same as 3, 4, 1, 2, 5, 6. The order of the rounds doesn't matter. And all of this is the same pairing. Another such pairing is 1, 3, 2, 4, 5, 6. 1, 6, 2, 3, 1, 6, 2, 4, 3, 5. This is another pairing. Alright? We need to find, this is a completely different pairing, this is a completely different pairing. We need to find number of pairings. Got it? Number of pairings. Is the question clear? Is the question clear? For example, the answer for 1 is like if there's only 1, then there are only 2 people here, n equals 1, 2 people, 1, 2. And there's only one pairing, 1 plays with 2, there's no other pairing. So for n equals 1, the answer is 1. For n equals 2, there are 4 people, 1, 2, 3, 4. So the answer for this is, what are the solutions here? 1 pairs with 3, 1 pairs with 2. One sec, I stop 1 sec. There are 4 people, right? 3, 4. What are the valid pairings here? 1, 2, 3, 4. This is one valid pairing. 1, 3, 2, 4. This is one pair. 1, 4, 2, 3. So the answer for this is 3. Now 2n choose to n factorial, 2n choose to by n factorial, are you sure? Because 2n choose to is just 2n into 2n minus 1 by 2 and this cannot be divisible by n factorial, so the answer is the answer can't be correct. Selecting any 2 out of them may be one way, like n choose 2, like there are 2n people, so it's probably 2n choose 2. 2n choose 2 is the first, it's the first step, like picking the first 2 people. But let's come to the example first. 1, 2 and 3, 4, 1, 3 and 2, 4, 1, 4 and 2, 3. There are only 3 valid pairings. Some of you might ask 1, 3, like say 4, 3 and 2, 1. This is also valid pairing, but no, this is already repeated here. Just that the order is changed and the order of the matches are changed, but we don't care about the order. The question says order of the rounds does not matter. Got it? Is this clear? Praful, you just wrote clear and you erased it. So is it not clear to you? Like, is there any part unclear? So what did we discuss here so far? N equals 1, answer equals 1. N equals 2, answer equals 3. Now for n equals, I won't write for n equals 3 because the answer is going to be huge. So, but I'll compute it in a smart way where the answer would be more clear. So for n equals 3, there are 6 people. Can someone tell me on the live chat what the answer for n equals 3 is? If you can compute it quickly. I'll compute it on the side too. So, first step, 6. Let's see what 6 can be paired with. 6 can be paired with either 1, 2, 3, 4 or 5. So 6 has 5 choices, right? 5. Now once 6 picks some number out of this, we have 4 numbers left. 1, say 3, let's say 6 picks 2. 6 picks 2. We have 4 choices, 1, 3, 4, 5. Now we need to make 2 matches between them. Let's say the answer for this is P1, answer this is P2. So P3 equals 5 multiplied by, now 6 picks one number. 6 picks one number. No, the answer is not 5. So 6 picks a number, say 6 picks 2. Now between 1, 3, 4, 5, you need to play 2 matches. So between 4 people, this is as good as between 4 people, we need to play 2 matches, which is same as P2. right? So 5 into P2 is 5 into 3, which is 15. What we did here is, we took the highest numbered guy, which is 6. Now, we matched it with one of the 5 people. The highest number guy has 5 choices. Right. We matched it with one guy. Let's call him 2. Or it could be 3 also. It could be 5, it could be 1, it could be 4. But we just selected 2. Now, there are 4 remaining people. Now, we need to play 2 matches between them. This problem sounds familiar like this. 4 people, we are playing 2 matches, which is the same as P2. So first guy has 5 choices. And the remaining, any 5 choices he chooses, there are 4 people remaining. Between them, you have to play 2 matches, which is P2. And it's 15. Now, is this clear so far? Any doubts? Alright. Now let's go to P4. Let's go to P4. How many people are there? 1, 2, 3, 8 people are there. 2 n people are there, as discussed in the question. 4, 5, 6, 7, 8. Now, the 8th person. 8th person. Is the previous one clear? Like P3 has 5 into P2? Alright. Now, can anyone tell what P7 is using this logic? Yes, exactly. Pawan, you're almost there. There's a slight, small change in your solution. Like your logic is correct, but there's a slight change in the answer. Just check your formula and tell me. Yes, exactly. When I got it right. Pawan also almost got it right. Good job. So, yeah, we repeat the same logic again. For P4, for 8 has 7 options. 7 options, correct? 7 options, which means that 8 can be matched with either 7, 6, 5, 4, 3. Let's say 8 is matched with 3. Let's say 8 is matched with 3. Now we have 6 more people, and we need to make 3 matches between them. And that sounds familiar to P3, right? We had 6 people. 6 people, 1, 2, 3, 4, 5, 6, and we have to make 3 matches. So P4, the number 8 has 7 choices. 7 into P3. Yes, Rahul got it right, the answer. So Pawan, Vinay and Rahul got the answers right. So 7 into P3, which is equal to 7 into 15. 105. Understood? So what we did here is, I'll just re-explain the logic in case it isn't clear. I'll just re-explain. P3, P2, it assumed. P2, the answer was 2. We knew the answer, it was 3. Also, if you look at it even more closely, P2, the number 1, 2, 3, 4. 4 has 3 options here. 4 can be matched with 3, 2 or 1. Yeah, correct. 4 is matched with 3, 2 or 1. So P2 has 3 options, and then once it's matched with one of them, we have 2 remaining. And 2 people remaining and 1 match. That's just P1, right? That's just 3. Now P3 is equal to 1, 2, 3, 4, 5, 6. 6 is matched with any of them. 6 is matched with 2. Now 1, 3, 4, 5 remaining. 4 people, we need to play 2 matches. Now this problem sounds familiar too. It's just P2. 4 people, 2 matches. So 5 into P2. P4, when I'll get to that. So how does such idea come out? Like, does it come by experience? Yes, it comes by experience. And this is a pretty famous form problem, so I didn't come up with this on my own. So I just saw when I was just reading up, I saw the solution. So, but this is not my own solution. So, but it's pretty. But if you're quite familiar, if you have done a lot of problems, it's pretty straightforward to come up with this. Like especially things like dynamic programming and thinking about it recursively. Like, how can I frame the bigger problem in smaller problems? That's what I'm doing, right? I'm framing P4 in terms of P3, 7 into P3. So bigger problem, smaller problem. All right. So it just comes by solving more and more problems. So yeah, there's no shortcut to it. Yep. Now similarly, P5, the number 10, 1 to 10, the number 10 has 9 options. 9. And once there are 8 people remaining and 4 matches, that problem Again, it's just P4, right? P4. 8 people, peeps, 4 matches. 4, sorry, people, 4 matches. Yeah. 9 into P4. So on. Is this understood? Like, any doubts so far? And similarly, Pn equals, there are 2n people. The 2nth person has 2n minus 1 options to match with. Correct? Now, once he matches with 2n, one of the 2n minus 1 people, there are 2n minus 2 people remaining. Meaning, and there are n minus 1 matches to be played with them. Since there are n minus 1 matches to be played with them, and we have 2n minus 1 choices, 2n minus 1 into p n minus 1. Yes, I'm explaining. That's exactly how it works. So P5 equals 9 into P4. Now, what is Pn? Pn equals, let's look at what Pn means. 1, 2, 3, so on till 2n minus 1, 2n. Now the 2nth person can be matched with any of the 2n minus 1 people. So the 2nth person has 2n minus 1 choices. Now after that person is chosen, like say 2n matches with say the number 3. Now there are 2n minus 2 people, 2n minus 2 people. Now there are 2n minus 2 people. Since one match is already played, here there are n minus 1 matches left. So 2n minus 2 people and n minus 1 matches. We know that this is same as P n minus 1. That's how the Pound's formula came. Is this clear? And now we know how to compute P n minus 1. P n minus 1 is equal to 2n minus 3 into P n minus 2. Like just substituting this here, that's it. And so on. Is this clear so far? Any doubts with this? Now if you look at this closely, any doubts, or Rajiv, or did I make that clear? And any doubts so far? This problem might be hard, but sometimes you just need to like what you need to think about what is happening when n is being incremented by 1. There are 2 new people coming, right? Now what can we say about the largest person? Let's say the largest person, the number with the largest number, he has 2n minus 1 choices, right? Any doubts so far? Like, do you want me to explain it again? Is there any part you want me to explain again? I'm really happy to explain it again. I want this to be clear for you. So the biggest person has 2n minus 1 choices. I'm just explaining you how to think. The biggest person has 2n minus 1 choices, right? Or any person has 2n minus 1 choices. Now we match that person and one of the 2n minus 1 choices. Now we take them and put them separately. We just put them up separately. They both are going to play a match, fine. Now what is, we have a smaller problem here, 2n minus 2 people. And we have n minus 1. And note that this is the same problem, but with less number of people and one less match. Two less people and one less match. And we know that now since we have reduced the bigger problem to a smaller problem, we can keep reducing it one by one till we reach the base case. That's what dynamic programming is about. I'm not teaching you dynamic programming, but that's how you need to look at it. That's like this needs to be one of your ideas. Even if it doesn't work out for a problem, you need to see like, you need to look at like just the smallest part of the problem, which is the person. Who is he going to be matched with? 2n minus 1 people. Now what after he matches? There are two people out of the scene. He matches with one person, 2 people are out of the scene. There are 2n minus 2 people. And n minus 1 matches. That's a smaller problem. Now bigger problem to a smaller problem. And once we reduce a bigger problem to a smaller problem, we can keep doing that till we reach 0. And we know the answer for 0. So we can build the answer from bottom up. Understood? You can do this too with practice. Is this clear? Awesome. Also, if you haven't subscribed to the video already, please do subscribe if you want to comment in the live chat. And If you think this video is going to be helpful to your friends, do share it to them, because I'd like the knowledge to be spread and they'll get better along with you, and you can discuss problems and you can get better together. Awesome. Now, let's just look at a sneaky way to calculate this. No, not sneaky, like it's the same way. So what is P5? P5 is 9 into P4. 9 into P4. P4 is equal to 7 into P3. P3 is just 5 into P2. P2 is 3 into P1. P1 is just P1 is just 1. Now what is P2? P2 is 3 into 1. It's just 1. P2, so P3 is 5 into 3 into 1. P4, 7 into 5 into 3 into 1. P5 is 9 into 7 into 9 into 7 into 5 into. P0 is again 1, but we don't care about it. So look at this. Now P6, similarly, P6, oh man, P6 equals 11 into 9 into 7 into so on till 1. So what is P5 doing? It's the product of the first 5 odd numbers. P4, product of the first 4 odd numbers. P3, product of the first 3 odd numbers. P2, product of the first 2 odd numbers. And P1 is the product of the first 1 odd number, which is just 1. Rajiv, please give an example on this concept in CF. I have to search, like, again, this is a pretty famous standard problem. So standard problems are not asked in CF directly. I'll search if you can find any. Ankit, and I just saw your message here. Thanks. Ankit, can you stop texting, because therefore you're spamming the chat. I just saw your message, and DP, it's gonna come up. It's gonna come up soon. Ankit, you're spamming the chat. I'd be happy if you'd stop it. Okay. So basically, Pn equals the product of the first n odd numbers, which is 2n minus 1 into 2n minus 3 into 2n minus 4, 2n minus 5 into so on till 1. Because the first n odd numbers are 1, 2, 1, 3, 5, so on till 2n minus 1. Right. So Pn is just the product of the first n odd numbers. Cool. Now, we are going to discuss another way to solve this problem. Any doubts in this? Any doubt in this topic? Any doubts in this topic? Like, is there any part of it you want me to re-explain? If it's clear, please tell me no. Please let me know if it's clear. Rahul, Rajiv, Vinay. Is this clear? Rajiv, I'll search for this concept. No worries. Okay. Let's look at another way. Now, what we're going to do is we're going to look at another way to solve this problem. So, what is the question here? There are n people, 2n people, n matches. So, what we're going to do is, the matches are going to look something like this: 1, 3, 2, 5, 4, 6, something like this, right? So, what do you see here? You see a choice of 2 people. Here you see another choice of 2 people. Here you see another choice of 2 people, right? All right. So, what we are going to do is, first we are going to order the matches and then divide by n factorial. That's what we are going to do here. This is going to focus on double counting. and how double counting is okay as long as you divide it by a factor. All right. So first, yeah, when I'm getting to it, one sec. Like first, let's discuss the problem first. So 1, 3, 4, 2, 5, 6, 4, 6. So what you're gonna do is first we'll just order the elements. We're gonna order the elements and order the matches. So for the first match, we have two choices. First match, we have two choices, which is two and choose 2. Right. First match, we have two choices. Second match, there are going to be n matches. First match, we have two choices. Second match, we have two people have gone. Now we have 2n minus 2 people, and we need to choose 2 people, which is 2n minus 2. Third match, 2n minus 2 more people are gone. So on. Correct. Now, what we do is, one sec, let me clear this crap out. Yeah. So what we do is, 2n choose 2, first game. 2n minus 2 choose 2, second game. So on. Last second game would be 4 choose 2. There will be 4 people left when there are 2 games left, into 2 choose 2. So on. So if we order the matches, we'd get 2n choose 2 into 2n minus 2 choose 2 into 2n minus 4 choose 2. So on till 2 choose 2. Got it? But this poses us a problem. What is the problem? We are ordering the matches, but the order doesn't matter, which means, what does this mean? When there are 6 people, for example, we have 1, 2, 3, 4, 5, 6. So what would we do here? The first game, it has 6 choose 2. Second game, 4 people are left, and there are two people we need to choose for the game. 4 choose 2. This is match 1, M1, M2, M3. 2 choose 2. So what is it like? So to conduct match 1, match 2, match 3, the number of ways to do it would be 6 choose 2 into 4 choose 2 into 2 choose 2. But since we are having the order, like we are deciding the order, we need to divide this by 3 factorial. Why? Because the order does not matter. Like we can play match 2 first and match 1 second, or match 3, any permutation of 1 to 3. And what's happening there is, like, we can see the double counting in action, which means, say we play the first choice, say we take 1, 3. Second choice we can take 2, 5. Third choice we take 4, 6. All right. But it can also so happen that we take 2, 5 first, 4, 6 first, and 1, 3 in the last. When you're multiplying all of them, it's counting this and this as two different choices, but we need to count them as exactly one choice. For example, we also are counting 4, 6, 2, 5, 1, 3. We are also counting 2, 5, 1, 3, and 4, 6. And there are other combinations as well. All 3 factorial combinations of, if you put this up, down here, like, one second, I'll just screw it up. Yeah. This first, this second, this third. We should not fix the order. We don't need to fix the order, but we are fixing the order only because it's easier for calculation. That's why we're fixing the order. But how do you remove fixing the order? Like, since this is coming once, this is coming once, this is coming once, this is coming once. So, and and two other combinations of this other, like I think 1 comma 3, 4 comma 6, 2 comma 5, 4 comma 6, 1 comma 3, and 2 comma 5. Each one is being counted. So this is being counted 6 times, but we need it to be counted exactly once. So what do? We just divide it by 6. If we divide it by 6, each choice would be each arrangement, each pairing would be counted exactly once. If we, that is 6C4, 6C2, 4C2, 2C2. If you just multiply this, each pairing would be counted 6 times. Since we want it to be counted exactly once, we just divide it by 6. That's it. Is this clear? Am I clear here? Any doubts with this approach? Do you want me to explain it again? I can explain it again. And you also see how you can see that this is equal to 15 or something. This is equal to 15. This is basically 15 into 6 into 1. Oh man. Yeah. 15 into 6 into 1 by 6, which is basically 15. Yeah, divide by 6 again. Correct. Is this clear so far? Any doubts? Do you want me to re-explain this, or if it's clear, can you please let me know in the live chat? Rahul, Rajiv, Vinay, Pawan, Praful, can you just like show it in the chat if it's clear? And others who are on the live chat, can you please? Yeah. Is this clear? Yeah. Awesome. Awesome. Oh, explain the divide by 6. Okay. So explain the divide by 6 again. Well, I'll just explain the divide by 6. It can be a bit tricky to understand. One sec. So 4 choose 2 into, yeah. All right. So first I'll explain it with the example of 2, then it'll be more clear. So for example, there are n equals 2. There are 4 people. 1, 2, 3, 4. Now, what are the, if you do 4 choose 2 into 2 choose 2, 4 choose 2 into 2 choose 2, like for the first game, you're picking 2 people. Second game, the remaining 2 people. If we do this, we get the answer 6. Okay. But we are double counting. Why? Because we're fixing the order of the matches. So 4 choose 2 into 2 choose 2, what all will this give? This will give you 1, 2, 3, 4. It will also give 1, 3, 2, 4. It will also give 1, 4, 2, 3. Fine. So far it's fine. But it will also give the first 4 choose 2. We can also pick 2, 3 in the start, right? 2, 3, 1, 4. It can also pick 2, 4, 1, 3. It can also pick 3, 4, 1, 2. Since we fixed the order of the matches, like 1, 2, 3, 4 is same as 3, 4, 1, 2. 1, 3, 2, 4 is same as 2, 4, 1, 3. 1, 4, 2, 3 same as 2, 3, 1, 4. So each pairing is repeated twice. 1, 2, 3, 4 is repeated again by 3, 4, 1, 2. This is repeating twice. Why? Because 1, 2, if you look at it closely, 1, 2, 3, 4, just the matches are being exchanged. The matches are being exchanged. 1, 3, 2, 4 and 2, 4, 1, 3. 1, 3 is being played second, 2, 4 is being played first. Because, but both are considered same because the order of the matches doesn't matter. Right? That's why you're dividing it. That's why you're dividing it by 6 by 2 factorial. Got it? Now, for the case of 3, what are you doing here is, in the case of 3, we had 1, 2, 3, 4, 5, 6. Since we had 3 matches, we are dividing it by 3 factorial because all the permutations of 3 factorial matches will occur. That is, if we pick 1, 2, 3, 1, 2 first and 3, 4 first, like this would be picked in say 6 choose 2, this would be picked in 4 choose 2, and 5, 6 in the last 2 choose 2. You don't really have a choice. There's only one way when you pick 4 numbers. This would occur 3 factorial times. For example, 3, 4 can come first, 1, 2 can come third, 5, 6 can come third. So all permutations of this will occur when you multiply this, right? Because you're fixing the order here. And that's why 6 choose 2 into 4 choose 2 into 2 choose 2. So each choice would come 6 times. But you want it exactly once. Like previously it came twice, here it's coming 6 times. Where did the number 6 come? All the permutations of this, like second choice can come first when you choose 6 choose 2, and so on. Third choice can come second choice can come first, and so on. That's going to happen if you label this as A, B, C. C can come first, B can come third, A can come second. All permutations of A, B, C. That's the number of times you have double counting. So we're dividing it by the double counting factor. It's 3 factorial. Is this clear? Now similarly, for 4 matches, there are 8 people. Four matches, right? First match, 8 choose 2. From 8 people, you're choosing 2 people. Second match, 6 people, you're choosing 2 people. Yes, the combination itself contains the permutation. Yep. 4 choose 2 and 2 choose 2. We multiply all of them. Third match, fourth match. So 8 choose 2 into 6 choose 2, 4 choose 2, 2 choose 2. But we divide it by 4 factorial. And why are we doing this? Because, for example, in the first choice, why are we doing this? The same reason we did it previously, which is, say in the first choice we choose 4, 5, second choice 3, 6, 2, 7, 1, 9. If we label this as A, B, C, D, we can see that if we multiply them, B can be our first choice, C can be our second choice, A can be our third choice, D can be our fourth choice, and C, A, B, D will also occur. But we need to count them as 1, all of them as 1, A, B, C, D, B, C, D, all permutations as 1. Which means that we need to count them as 1. But if we do this, we're counting them 4 factorial times. All permutations will occur exactly once, right? So we're counting them 4 factorial times. So this would ask us to 8C2, 6C2, 4C2, 2C2. This would mean, since each one is being counted multiple times, that is 4 factorial times, we divide this number by 4 factorial to get the correct answer. Got it? Any doubts so far? Drop it in the live chat. I'm just looking at it. So for any given n, it's basically, we are ordering them for n matches, 1, 2, 3, 4, 5, so on till n. First one we have 2n choose 2. Second one, 2n minus 2 choose 2. 2n minus 4 choose 2. So on, 2 choose 2. Last match you won't have any choice because all of them would be done. Awesome. It's glad to see that everyone understood it. I really want you guys to understand it. Guys and girls, yeah, everyone. So what we do is we multiply everything. 2n choose 2 into 2n minus 2 choose 2 into 2n minus 4 choose 2, so on till 2 choose 2 by n factorial. Because there are n matches, each choice would be occurring n factorial times. Got it? Now, we computed this. Let's simplify this further. So what is 2n choose 2? So 2n choose 2 is basically 2 2n factorial by 2 factorial into 2n minus 2 factorial into 2n minus 2 whole factorial. This is basically 2n minus 2 factorial into 2n minus 4 factorial into so on. So what do we get here? 2n minus 2 factorial, 2n minus 2 factorial cancel, and 2n minus 4 factorial will cancel from the 2n minus 4 factorial coming from 2n minus 4 choose 2, right? So what do we get in the end? What do we get in the end? So 2n choose 2, 2n minus 2 choose 2, 2n minus 4 choose 2, 2n minus 6 choose 2, so on. So here we get 2n factorial by 2 factorial into 2n minus 2 factorial, correct? This 2n minus 2 factorial by 2 factorial into 2n minus 4 factorial. This 2n minus 4 factorial, 2 factorial into 2n minus 6 factorial, so on. Here you can see that 2n minus 2 factorial, 2n minus 2 factorial cancel, 2n minus 4 factorial, 2n minus 4 factorial cancel. Exactly, Pawan's right, yeah. Already, I think, yeah, Pawan is right, and I think Vinay also mentioned it before. So 2n minus 6 factorial, 2n minus 6 factorial will be cancelled. So all you'll have is all 2 factorials in the denominator. In the end also, 2 factorial will be cancelled in the new, like 4 factorial by 2 factorial, 2 factorial, 2 factorial by 2 factorial into 0 factorial, right? 2 minus 2 is 0. So 4 would be cancelled from before, and this 2 factorial will be cancelled from here. So we get 2 factorial, 2 factorial. So you get 2n factorial by 2 factorial. 2 factorial is coming n times here, n times. 2 factorial to the power n. Now we note that we divided all of this by n factorial again, n factorial, because of double counting. So this is the solution. 2n factorial by 2 factorial into power n into n factorial. Now, how is this equal to our last solution? Turns out it is. Let's look at it. So this is basically 1 into 2 into 3 into 4 into 5 so on till n by 2 factorial whole power n into 1 into 2 into 3 into 4 into so on till n. Alright, let's not cancel into n. Sorry, this is still 2n. Numerator is still 2n. Denominator is 2 factorial power n into 1 into 2 into 3 so on till n. Now, let me drink some water. Now, what are you going to do is, there are n 2's here. This 2 factorial is same as 2 power n. First 2 we multiplied by 1, second 2 we multiplied by 2, third 2 we multiplied by 3, so on. And what will you get? Upper will get 1 into 2 into 3, so on till 2n. Denominator will get 2 into 4 into 3 into 6 into so on till 2n. Because each 2 we are multiplying 1 by 2, we are multiplying 2 by 2, because there are n 2's here. And the first n numbers we are multiplying it by 2. So that takes away all powers of 2. First one we are multiplying it by 2, second one we are multiplying it by 2, so on. Now, the numerator we have the product of first 2n numbers. The denominator we have product of first 2n, like all the even numbers up to 2n. So if we take all the even numbers up to 2n from 2n factorial, we are left with all odd numbers. 2n minus 1. Yeah. So this would give us 1 into 3 into 5 into 6 into 7 into so on till 2n minus 1. All odd numbers up to 2n minus 1. Because 1 into 2, yeah, I'm from BITS Goa actually. Yeah, not from Pilani. So 1 into 2 into 3 into so on till 2n, first 2n numbers divided by all even numbers up to 2n. You're taking away all the even numbers from the denominator and you're left with the odd numbers. That's what's happening here. 1 into 3 into 5 into 7. So on till 2n minus 1. Now note that in the previous way of solving the problem, we arrived at the same solution. Pn equals 2n minus 1 into Pn minus 1 and so on. In the previous problem as well, we got Pn equals 2n minus 1 into 2n minus 3 into so on till 1, right? And here also we got the same thing, 1 into 3 into 5 into so on, 2n minus 1. So did you understand this so far? By doing this approach as well, we got the solution as the product of the first n odd numbers. Is this clear? Any doubts with this? Any doubts so far? I'll be happy to like explain it again. Do you want me to explain any part of this question again? I want this to be clearly embedded into your head. How do you solve this? Yeah, how to solve this. And again, how would you arrive at the solution? So similarly, how you would arrive at the last solution. Again, look at it closely. Like there are n matches. For the first match, how many choices do we have? How many choices do we have for the first match? From the 2n people, we can pick any 2 people, right? I'm just telling you how you could arrive at the solution if you were given this problem. Yes, we arrive at the same result by doing it 2 different ways, correct? Because both ways are correct. You have to arrive at the same result because both ways are correct. So how would you arrive at this result? So in this question, there are 2 things, people and matches. In the previous question, we looked at one person. What does one person have to do? They have to connect with any of the 2n minus 1 people and so on. And the next person of one of the 2n minus 2 people, we are arrived at a smaller problem. Now, in this solution, what are we doing? What is the smallest problem here? The smallest thing here, match. What happens in a match? 2 people compete. And those 2 people, they have to be taken from the 2n people, right? Not 2n choose 2. Now there is another match, second match. 2 people are gone. In second match, 2n minus 2 choose 2n you need to pick 2 people from the remaining 2n minus 2 people, right? So 2n minus 2 choose 2 and so on. Now once we have the matches, we look at the question again. The question it's mentioned that we shouldn't order the matches. Here we are ordering the matches. So since we shouldn't order in the matches, order doesn't matter. We see how many times we're double counting here. So 2n choose 2, 2n minus 2 choose 2, so on. If we do that, different orders of the same pairing can occur multiple times. Like the same pairing will occur in different orders. How many orders? N factorial orders, because there are n factorial ways to order the given match set. And that is how, and at this point that you multiply all of them, and then you need to divide it by the number of times each order is being permuted. Like that's n factorial. That's why you're dividing by n factorial. Awesome. Is this clear? Any doubts so far? Know that we arrive at the same result. So Durgesh is in a better college. Good for you. Awesome. Any doubts so far? Do you want me to re-explain any part of this? I'd be happy to re-explain. Clear? Any doubts so far? Any questions that you're facing? Yeah, Pinash is clear. Awesome. Now, let's look at another approach. This is going to be a bit hard, and this is going to be slightly hard. And it's probably hard to come up with the solution as well. So it's okay if you don't come up with the solution. Rajiv, like if you look at it, this is the problem. This is the question. Like this is an example of its approach. Like this is a problem in itself. So I mean, you could call this an example, honestly. Or is there something more specific you want? Can you mention it in the chat so I know? Because this is a problem on its own, and it's an example of the concept that I'm teaching. So, is there anything in specific you want me to focus on? So, again, look at the question. There are 2n people, n matches. Now note that we know two approaches to solve this problem, and these approaches can be solved at different problems as well. So 2n people, n matches. Now what are we going to do? We're going to list those 1, 2, 3, so on till 2n people. Alright, we're going to list them. We're going to write them in the order, in any order. Like we can write 3, 2n, 1, 2, 5, so on till 11. So anything. We're going to permute them. Shuffle. Vinay, I'm not sure, like, I know at least I'm probably going to teach for the next month at least. So, yeah, that's a start. 11. So on, right? Now 3 to n, 1, 2, 5, any permutation. Okay, we look at this permutation now. Now we are going to do similar to the last approach. This is the previous approach, very similar. We're going to pick the first two and add them to the first match. Next two and add them to the second match. And you'll get an arrangement, you'll get a choice, you'll get a pairing, valid pairing. For example, for n equals 3, I'll actually do it for n equals 2 first. N equals 2, you have 1, 2, 3, 4. We take any permutation, 2, 4, 3, 1. We list down all permutations, 1, 3, 4, 2. I'll just write another number, 1, 2, 4, 3, 1, 3, 2, 4. There is going to be a lot of repetition here, but we're going to eliminate that later. 3, 1, 3, 2, 1, 4. So on. All right. 2, 4, 3, 1, so on. Now, we pick the first two, second two, and we put them in the match. 2, 4, 3, 1. There's going to be repetition here, but we're going to eliminate that later, and so on. There are going to be a lot of permutations. 1, 2, 4, 3. We already have a repetition here. 1, 3, 2, 4. There's already a repetition here. And there are going to be a lot of repetitions. That's okay. And in this, you're going to match 3, 2, 1, 4, and so on. Now what? So, what do we get now? Like, we are going to make matches in this way. This is how we're going to like make pairings. So we list down all permutations, and for each permutation we write a pairing. And we know that we have 2n factorial permutations, correct? And we say that this is one pairing, this is one pairing, this is one pairing. But note that each pairing occurs a lot of times. For example, one sec, I'll just clear this part out in the end. We'll just look at how many times one pairing occurs. So 2, 4, 3, 1 occurs as, it's going to repeat as 3, 1, 2, 4. This and this is the same thing. This will give you 2, 4, 3, 1. We are counting this as 1. We are counting this in 2 factorial, in the 2n factorial permutations. Like, we are mapping permutations and pairings. Okay, that's what you're doing. Now 3, 1 and 2, 4. We get 2, 4, 3, 1. We are counting this once in 2n factorial, but we shouldn't. But we'll get to that later. We'll divide it by a number. Like, no worries. We are just trying to find what number we are going to divide it by. We know that each pairing occurs a lot of times, We are calculating how many times it occurs so that we can divide it by that number. Okay. So 2 comma 4, 3 comma 1, 2 comma 4, 3 comma 1, it's occurring. Now 4 2 3 1 is also a permutation, right? 4 2 3 1 is also a permutation of 1 2 3. This in this also 2 comma 4, 3 comma 1. This is being matched. Now 4 2 1 3 is also permutation, right? This is also 2 comma 4 is being played, 3 comma 1 is being played. Again 3 comma 1, 4 comma 2. This is also a permutation, right? This is also permutation. And this is also going to yield 2 comma 4, 3 comma 1. So a lot of permutations are mapping to the same assignment. Or a lot of permutations are mapping to the same pairing. This is mapping to this pairing. This is also mapping to this pairing. This is also mapping to this pairing. A lot of permutations. Right? Now how do we count how many permutations? 3 comma 1 from 4 comma 2. What else is left here? 3 comma 1, I guess 1 comma 3, 2 comma 4, 1 comma 3, 4 comma 2. All of them. I'm just listing them down so that it's more clear. What else is left? There's one more thing left. 2 comma 4, 1 comma 3. You can see that all the like 1 3 2 4, 1 3 4 2, 2 4 1 3. All these 8 permutations are mapping to the same assignment. Can you see that? And if you look at it closely, you can't give more permutations which map. There are exactly 8 permutations of 1 2 3 4 which map to the same valid pairing. If you look at it, is that clear? How is this happening? Like, so what we do here is, since 8 permutations are mapping to one pairing, 2n factorial permutations will map to 2n factorial by, that is basically, there are 4 factorial permutations, right? 4 factorial permutations. 8 permutations are mapping to the same pairing. 4 factorial permutations will map to 4 factorial by 8 pairings. Yes, it's 2 factorial into 2 factorial into 2 factorial. Yes, that's exactly where it came from. I'll show you how. Now, where did this number 8 come from? I'll show you. Note that this is a bit hard, like, but I'm still teaching. If you get it, that's really awesome. I'll still clear your doubts nevertheless. So, where did we get this? 1, 2, 3, 4. In a permutation, you can see that any permutation 3, 2, 1, 4. These two can be interchanged. These two can be interchanged, like 2, 3, 1, 4, 2, 3, 4, 1, 3, 2, 4, 1. All these will map to the same permutation, correct? Which means you can interchange these two, which means 2 square already, which is basically, I'm just writing the double counting factor here. 2, you can interchange these two and it will give you the same pairing. We can interchange these two, we'll get the same pairing. Now, we can interchange these two as well and get the same pairing. That is, we can get 1, 4, 3, 2. 1, 4. If we interchange these two, we get 1, 4, 3, 2. If we interchange these two, we get 1, 4, 2, 3. If we interchange these two, we get 4, 1, 2, 3, so on. That's where we can interchange between these two as well. That's where we'll get the same ordering. That is why that's where the other multiplication of 2 comes from. Since that's how all 8 will map to the same pairing, correct? All right. So, what did we do here? We wrote down all permutations and we mapped them to a valid pairing. Now we saw that for a given permutation, the first two, we're taking the first one mapping, next one mapping, first one making them a match, second one making them a match, so on. But a lot of permutations are leading to the same pairing, right? This is leading to the same pairing as this, as this, and so on. But how do we get to the number 8? So in the first, if you interchange, you'll get some permutation and that will give you the same. The first two, if you interchange, 3 comma 2, 2 comma 3 you're going to get the same pairing. 1 comma 4, you can interchange them and you'll still get the same pairing. And this first two, if you change the next two, like the first two, bring them here, that will be the same pairing because the order does not matter. That's where the first two is because we can interchange any of the first two and we'll get the same pairing. Second two, the next two is because you can interchange any of the next two and we'll get the same pairing. And this two is because you can interchange the first two with the second two. And that will give you the same pairing. That's where the double counting factor 8 comes. So the total number of valid pairings would be 4 factorial by the double counting factor, which is 8. 24 by 8, which is equal to 3. As you can see, it's P2. P2 was the product of the first two odd numbers, 1 into 3. We got the same result, as you can see here. Got it? Now let's do it for larger numbers. Is this clear so far, what I've done so far? Any doubts with this? Any doubts with this so far? If it's clear, please let me know it's clear in the live chat. I'm just staring at it. Yeah. Awesome. Thank you. Thanks, Paul and Rahul. All right. Now, for 3, let's look at it for 3 and then let's generalize it for n. Now, for 3, what are we doing? 1, 3, 4. We are listing down all 3 factorial permutations. Sorry, 6 factorial. So 3, yeah, 6 factorial. 3, if n equals 3, there are 6 people. 1, 2, 3, 4, 5, 6. What are we doing here? We are listing down some permutation, all permutations, and we are pairing the first two. Let's take some permutations. 3, 5, 2, 1, 4. Got it? 3, 5, 2, 1, 6, 4. Now we are pairing up the first two, pairing up the second two, pairing up the last two. 3, 5, 2, 1, 6, 4. Note that, like similarly to the last problem, a lot of other permutations are going to map to the same pairing. For example, 5, 3, 2, 1, sorry, 5, 3, 2, 1, 6, 4. There are totally 6 factorial permutations, and each permutation will lead to a pairing, and multiple permutations will lead to the same pairing. For example, this permutation is leading to the same pairing because 5 and 3, 5 plays with 3 and 3 plays with 5 is the same thing. So on. We are trying to find the double counting factor again here. What is the double counting factor? How many times is each pairing occur? Each pair, how many permutations map to the same pairing? Let's look at that. So 5 comma 3, and we can interchange 3 and 5 in this permutation and will map to the same pairing. 2 and 1, we get the same pairing. 6 and 4, we are going to get the same pairing again. So we can interchange any of these two and we'll get the same pairing. So that's 2 into 2 into 2. You can interchange any of them and get the same pairing. And additionally, we can bring this first and bring this second. For example, you can bring 2 comma 1, 3 comma 5, 6 comma 4. Yes, 2 factorial power n into n factorial. That's correct. This is 2 cube here. Correct. We can interchange any two, and we are going to map to the same pairing. Yes, 8 into 3 factorial is exactly correct. Let's tell it more clearly. 5 comma 3 you can interchange, 2 comma 1 you can interchange, 6 comma 4 you can interchange. All right. Now we can interchange this whole thing together as well. Yes, you all are exactly correct. I'm so glad you found it. Now we can interchange. For example, 2, 1, 3, 5, 6, 4. Also 6 comma 4, 2 comma 1, 3 comma 5. How many of them are there? If you call this A, B, C, you can interchange any of those pairs. You can bring the third pair first and first pair second, second pair last. All and several other things. And all of them will lead to the same valid arrangement, same valid pairing, which is this. Correct. As long as you don't mingle from one pair to another, like if you don't take elements from one pair and put it in the other, as long as you don't do that, you're going to reach the same valid pairing, right? You just need to. So there are two types of double countings that are happening here. One is within pair you can change order, like first second or second first, and we have n such pairs. That's why we are multiplying it by 2 cube, 3 such pairs, 2 cube. And we can change the order of the pairs. You can bring the second pair first, first pair second, last pair first, second pair last, and so on. Since all those n factorial things are mapping to the same valid pairing, we're going to that's going to be added. So that's going to add to our duplication factor, which is 2 power 3 factorial. And from this we get, so 6 factorial is our total permutations, and 2 cube into 3 factorial, which is like 48. 48 permutations mapped to the same pairing, which means 6 factorial permutations will map to 6 factorial by 48 pairings. That's our answer. 6 factorial is 720. 720 by 48 is just 15. 15 is 1 into 3 into 5, if you remember correctly. Is this clear so far? Any doubts? Any doubts? So what this means is, for 3, we got to know that the answer is 6 factorial by 2 power 3 into 3 factorial. This is basically for given n, we can list down all the 2n factorial permutations, 2n factorial permutations, and divided by 2 to the power n, because there are going to be n pairs, and in each pair the first 2 you can rotate and it's going to be the same order, same pairing. Next 2 you can rotate and you'll reach the same pairing, and so on, to power n. In 2, you can shift the order of the pairs. You can bring the first 2, second 2, third 2. There are n such pairs, n such matches if you look at it. And n such matches you can order them anyway because order doesn't matter. N factorial. That's it. Answer for n. Is this clear? Did everyone understand this? I need you all to understand this. It's hard, I understand, but like it might be a bit tricky at first. But if you understand it, then that's really great. That's really great. Note that in the last problem as well, we got, if you look at the last problem, we got the same thing, right? Yes, Pawan, I know this intuition is hard to get. I just told it so that, what do you say? But it's sometimes used in harder problems. This kind of this approach is sometimes used in harder problems, harder combinatorics problems. I just told it so that sometime, if you get a hard problem, just in case this approach strikes to you, I'll be really happy. Like that, it might strike. I'm not telling it will strike, but it might strike. That's going to be really great, right? Bishwa Ranjan, can you explain which part you want me to repeat? So what I did here was, for 2 we saw the answer was 4 factorial by 2 factorial into 2. For 3 we saw that the answer was 6 factorial by 2 cube into 3 factorial. So what we did was we generalized it for n people. Like how does the solution look for n people? For n matches. So for n matches there'll be 2 n people. And what did we do? For each permutation we made a pairing out of each permutation. And how did we make the pairing? We matched the first 2, the next 2, the third 2 people. Like for example, if there are 6 people, 3 matches, 1, 2, 4, 5, and 3, 6. We match 1, 2, 4, 5 and 3, 6. Now, we are doing this for all the 6 factorial permutations. But there are a lot of repetitions, which means multiple permutations are mapping to the same valid pairing. And that is bad because we want the exact number. We don't want the duplicated number. So we need to divide this 6 factorial, the number 6 factorial, by a duplication factor. And what is the duplication factor? We found how many times, how many permutations map to the same pairing, and we divided it by that number. And what is that number? So first two we can rotate, first two we can exchange, and we're going to get the same permutation. Second two we can exchange, third two we can exchange. We can exchange them independently. That's why I'm multiplying. We can do all of this independently. Like we can exchange this, we can exchange any subset of numbers, say subset of pairs. Like we can exchange first pair, third pair, fourth pair, and so on. And we can reorder them as well at the same time while exchanging. All of these operations are independent, and that's why we are multiplying them. This is going to be 2 cube into 3 factorial. 2 cube is we can interchange between the pairs, and we can reorder them. That's where the 3 factorial comes from. Reordering them gives the same answer because the order does not matter. And the same thing we're doing for n numbers. N matches and 2n people. We get this. And note that we got this in the last question as well. 2n factorial by 2 power n into n factor. We got this while computing 2n choose 2 into 2n minus 2 choose 2. So on by n factorial. This is what we got in the last question, and the answer is exactly same. This and this is the same. We discussed how we got to this, in the last question itself. Rewind the video and see. Like we expanded this and we cancelled out the numerator and denominators. Yeah, the final result is the exact same. Just that the approach is different. Now what? Okay, wait. One sec, something's wrong. All right. So we saw that 3 different approaches. The first approach, we got the answer as product of first n odd numbers. Second approach, we got the number as 2n choose 2, 2, n minus 2 choose 2, 2n minus 4 choose 2, so on by n factorial. N factorial was the limiting of the duplication factor there. Third approach, we got it as 2n factorial by 2 power n into n factorial. We saw how this was equal to this, and we can also see how this is equal to this. We just computed it. 2n factorial is the product of the first 2n numbers. Denominator is 2 into 1 into 2 into 2 into 2 into 3. I'm just adding 2 to each number. So until 2 into n, right? 2 into 1, 2 into 2, 2 into 3. So this is numerator is 2n factorial. Denominator is product of the even numbers under all even numbers under 2n. So if we cancel stuff from this, we get, like, from the first 2n numbers, we are removing first 2n, the even numbers under 2n. So we are left with the odd numbers under 2n. So this is same as product of first n odd numbers, or product of all odd numbers under 2n. Easy. This is same as this. This is same as this. So we got 3 approaches, 3 very different approaches to the same answer. Got it? Any doubts so far? I'll just quickly explain how you could code this very quickly. Say you're given t test cases, and in each test case you have to take in a number n. Int n. You don't need to compute factorials or anything. You don't need any of this. Since we know that the answer is so one way we could do is product of first n odd numbers. Say we want to calculate the answer modulo prime number, which is mod. How do we do it quickly? Answer equals 1. For int I equals 1, I less than n, less than equal to n, I plus plus. Actually, I equals 0. Oh, sorry. Yeah. Answer is answer equals answer into ith odd number is 2 into n minus 1. 2 into I minus 1, right? C odd. Answer. But this solution is going to take O of n into t time. This is basically the product of the first n odd numbers. That's a solution. Like we just need to print the answer for one solution, right? We don't need to like. I'm just doing this part. What are the first n odd numbers? That's a solution. How do you do it quickly? This is O of n into t. If you look at it, O of t. If t is up to 10 power 5 and if n is also up to 10 power 5, this is going to take 10 power 5 into 10 power 5 time. O of n into t. That's not favorable for us. How do we do it quickly? Let's pre-compute the answers. O of 10 power 5 into 10 power 5 is 10 power 10, which usually falls out of time limit. How do we do it quickly? Let's pre-compute using, I mean, you can call it dynamic programming, but it's whatever you call it. Int ll answer for maxim. Let's check this out. Let's pre-compute. For all numbers, answer of 1 equals 1. All numbers from 2 to I less than maxim, I plus plus, you can pre-compute the product. Exactly. Answer of I equals answer of I minus 1 into 2 into I minus 1. We discussed this. Answer of n equals 2n minus 1 into answer of n minus 1. Our very first approach. Don't forget to take modulo. Now so we can just directly see out answer of n. That's it. So this is O of 10 power 6, which is under time limit. This is O of t. At each test case, we're computing exactly once. O of 1. O of t plus n, which is very straightforward. Like it's going to pass basically. Understood? One sec. Exactly, you can pre-compute the product. That's what we're doing here. Answer of I will now contain the product of the first I odd numbers. For example, answer of 2 will be answer of 1 into answer of 2 into answer of 2 will be answer of 1, which is 1 into 3. Answer of 2 will be answer of 3 will be 5 into answer of 2, which is 5 into 3, which is 15, so on. Is this clear? Any doubts so far? Any doubts? Do you want me to re-explain something? If it's clear, I can end the class. Is this clear? Awesome, guys, guys and girls. So if it's really clear, then I saw it in the I saw a few comments in my last video where people asked me to take upsolving sessions, and on that request, I would be taking upsolving sessions, and they will be coming soon. So yes, and that would really help to increase your rating on Codeforces or increase your competitive programming skill in general, because upsolving is where the learning happens. And yep, I saw that, and I want to finish this first. Like I want to finish maths first. As I said, maths is the real base for competitive programming. It's one of the most important topics in competitive programming. So yeah, and all right then, I'll see you in the next class. So awesome. Also, if you haven't subscribed to this class already, I suggest you to subscribe to this channel, and also do check out the Career as a Software Developer subscription. So use the code SciLive. Awesome. Then see you in the next class. Goodbye. My next class will be about problem solving and combinatorics. As you can see, the live class already up. All right. See you then. Have a nice day. Any doubts, please put it in the comment section. I do take a look at the comment section.